Hi folks, last set of landforms now in the Unit 4 video series. We've looked at intrusive volcanic features, extrusive volcanic features. We're now looking at seismic features. Three types in particular: folding, faulting and earthquakes. Start with folding. Now folding occurs at convergent boundaries. The reason for this is that plates are coming into each other and they're folding up. If we've got two continental Sial based plates, neither's going to subduct under the other, so they're going to push and they're going to crunch into each other and they're going to fold up, forming fold mountains. In terms of the folds that you get anticlines and you get synclines. An anticline is where you've got a hump, a syncline is where you've got a dip. Think of it this way: anticline is this kind of shape, like an A-ish, but without the bar. So anticlines have A shape, synclines are a dip. There's no rhyme or reason as to how many anticlines, how many synclines you'll get, but it's like when a car crashes into something, the bonnet all folds up. Same sort of idea here. Where we've got a Sial and a Sima plate coming together, an oceanic and a continental, in other words, the Sima oceanic plate, being more dense, will subduct underneath the Sial continental plate, but it will cause folding. The Sial plate is less dense, so it's less strong and will fold up, whereas the more dense Sima plate will simply warp and go underneath without folding. What this does is it creates a trench between folded up possibly hills, possibly mountains, and the Sima plate. So going down and it creates this gap, and that gap, that's all folded up, that gap is the trench. That trench, such as the Mariana Trench, can be very deep. It also lets in water. That's how the water gets in and gets into the magma, and this part of the plate begins to melt. Incidentally, the folding is also the reason why sometimes the magma has a very long way to go before it can extrude as lava. So once this melts, it has to go up. There has to go kind of a longer way because of all of the folding, which can mean it picks up more silica and the rock becomes more rhyolitic once it's formed a volcano. So that's folding. To recap, it's where plates push into each other and fold up. This is a seismic event because there's no volcanoes involved. There's no magma involved, not directly anyway. It's all to do with just the movement of plates, the tectonic shift, which means it's a seismic feature. Much like faulting. Folding is where they crunch together, faulting is where they break apart. If we look at a divergent boundary, a convergent boundary and a transform boundary, they all have elements of faulting. Let's look at each one in turn. Divergent boundary creates a rift. That'll be along a ridge. This is where the plates pull apart from each other and blocks of those plates drop down. There we go. Drop down away from the surface. So it pulls away and bits drop into the middle in a kind of stepped version, much like the East African Rift Valley. This is called a normal fault. I don't know why it's called a normal fault, because it's no more common or less common than any other. But what happens is, you can see here, the plates are pulling away from each other and it creates a plane like that. So they pull away like that because parts are falling in to the trench, into the rift, sorry. That's a normal fault. where they're pulling apart. If they're pushing together, you get a reverse thrust fault. This is where two plates are pushing together, as well as folding, they are going to slide over the top underneath each other like so. So when they're pushing together, it's a reverse thrust fault, and it creates quite a steep cliff side, as you can see from here. This is the sort of fault that was at the Sichuan earthquake. So that's normal, that's reverse thrust. In terms of features, they both create cliffs, but they look quite different. This is going to create trenches, this is going to create cliffs and rifts. The transform boundary, well, it depends partially on which way the plates are moving. If it's like the San Andreas fault, where they're both moving in the same direction, or whether the plates are moving in different directions, you end up with slight differences, but it rarely is anything beyond what we just call displacement. I.e., imagine you had a fence running along here. As the fault shifts, the fence will be broken apart and displaced. You see that quite a lot in California. You don't get rifts and ridges because nothing's pulling apart. So you don't get normal faults. You don't get reverse thrust faults because generally things aren't pushing together. What you do tend to get though, like with the San Andreas faults, is you just get some displaced earth, and in a sort of a long pattern you get this sort of disturbed, ruckled up kind of look. The San Andreas fault is a perfect example. So to recap these, normal faults, pulling apart, reverse thrust, pushing together, transform, sliding past each other. Each one creates a different landform. In terms of which ones are more distinctive, rift valleys are pretty distinctive, as are trenches. Transform faults, maybe less so, but San Andreas can be seen from space. So these are the big two, faulting and folding, very, very visible. Next up we have earthquakes. Earthquakes cause displacement. It's generally on quite a small scale, because an earthquake is from one focus point of pressure that's released, but it can be quite dramatic. The impact of an earthquake depends on how deep the focus is. If it's at a convergent boundary, you've got a whole length of plate for pressure and friction to build up, which means you can have shallow, medium or deep focus earthquakes. At a transform boundary, because the plates sliding side by side, you're generally limited to shallow focus earthquakes only. You don't get earthquakes really, might get tremors, but you don't get earthquakes really at divergent plate boundaries. There's no friction being generated. Now, depth of focus changes how the earthquake reacts. Firstly, at a convergent boundary, the deeper the focus, the further back from the plate boundary you will find the epicenter. The epicenter, of course, being the point directly above the focus where the energy is measured from. Shallow focus earthquakes are going to be much closer to the plate boundary because they haven't gone as far down on the angle. Transform boundaries, though, being all shallow focus, generally focus will be being directly beneath the epicenter. It's not going to be any distance from the plate boundary. So that's the first thing, to be distance from plate boundary. Secondly, more importantly, is the amount of shaking that you get. The deeper the focus, the less shaking you get. The reason for this is because of the two types of waves that are given off by an earthquake. When an earthquake is triggered, the first wave it gives off is the primary wave, the P wave, and this goes out in every direction. As well as being primary, it's also a pulse. It goes through the ground. It doesn't create much shaking, but it moves very, very fast. You can pick it up quite a long time ahead of the next stage, which is the S wave. And that's good because that pulse isn't going to do much damage, but it'll warn you that there is shaking that's about to happen. Because next up comes the S wave. S stands for secondary, but it also stands for our purposes, shaking. Remember, S, shaking. It follows exactly the same route, but it moves much slower. And this is a sine wave shape, up and down. So rather than being a pulse going all the way through, it's up and down. And that's a big problem, because that's what damages buildings. It shakes them and breaks them apart. The deeper the focus, the more rock those S waves have to travel through. And the more rock they have to travel through, the more the energy is lost. So first off, it means that the energy is being depleted, whereas in a shallow focus earthquake, there's still loads of shake energy that can be sent out. So you get much more shaking at a shallow focus. Also though, at a deep focus earthquake, you get more time, you get more warning, because you'll get the pulse, which moves very fast, followed by the S wave, which moves much slower. If you've got more distance, the two have got more time to split up from each other, so you've got more warning. It's one of the things that Japan has developed very well, picking up the P wave and then warning everyone, because generally they get deeper focus earthquakes. So what does this mean? Well, it means that a shallower focus earthquake will cause more shaking and more disruption to the landscape. It also means that people will not have time to react in the same way, which means that from a human point of view, which admittedly is not as important in this report, but it's still worth knowing, from a human point of view there'll be more destruction done potentially, so the human landscape will be affected more because people will not have time to prepare. Deep focus earthquakes tend to be much less shaking involved. The only counter to that is that deep focus earthquakes, because they are very deep, they tend to release a lot more energy. So compared to shallow focus earthquakes, they tend to release a lot more energy, which means you get a bigger pulse and then a bigger secondary wave. So you might get a very deep focus earthquake that released a huge amount of energy, and that will cause a large amount of shaking just because of the sheer amount of energy. But if you think of it in terms of amount of shaking that you get for the amount of energy the earthquake releases, a shallow focus is the most efficient earthquake. So to recap those, the shallower the focus, the closer to the plate boundary. The shallower the focus, the more shaking from the secondary wave, and the less time warning you get from the primary wave. So overall, in terms of the effect on landforms, earthquakes can do small scale disruption, and if it's a shallow focus one, it can create a lot of disruption. But faults and foldings create big intercontinental landforms. We will briefly look at secondary landform impacts of volcanic and seismic activity, and then we will look at how you can put this into your report.